Digital LCR meter. In this LCR meter, which is useful to measure the inductance, capacitance or resistance values, are indicated by means of digits. LCR meter or bridge is used for measuring inductance, capacitance and resistance. LCR meters are items of test equipment or test instrumentation used to measure the inductance, capacitance and resistance of components. LCR meters are often used for inspection to ensure that the components arriving are correct. They can also be used in a development laboratory where it is necessary to test and measure the true performance of particular components. The LCR meter or LCR bridge takes its name from the fact that the inductance, capacitance and resistance are denoted by letters L, C and R respectively. Some versions of the LCR meter use a bridge circuit format as the basis of its circuit, giving the name that it is often used. Simpler revisions of LCR meters provide indication of the impedance, only converting the values of inductance or capacitance. More sophisticated designs of LCR bridge are able to measure the true inductance or capacitance and also the equivalent series resistance and the tandem of capacitors, that is the dissipation factor and the Q factor of inductive components. This makes them valuable for assessing the overall performance or quality of the component. The LCR bridge measurements, the guidelines are to make the best measurements using an LCR meter. Few guidelines or hints and tips those can be employed are the effect of lead length. As we know, at high frequencies above 1 megahertz or so, the lead length can start to have an effect. So for best measurements, leads must be kept as short as possible. Next, measure at operational frequency. When making measurements using LCR meter, it helps to use a test frequency as close to the actual operation frequency for which it will be used. Adjust test amplitude. Same as the reason mentioned for operation frequency, it's better to test the component with an input signal. The amplitude is same as for which it will be useful or it will be used in the circuits. Next thing is we have to discharge the capacitors before measurement. Some capacitors may carry a residual charge under some circumstances. So it is best to discharge before any measurements. LCR meters can also be used as an aid for fault finding. LCR meters are most often used to display the capacitance, inductance, and resistance, but may also be used to measure the Q of an inductor or tandle of a capacitor. As such, they are particularly useful items of test equipment. So now let us see the so this is the block diagram of a digital LCR meter. An LCR meter is a piece of electronic test equipment used to measure inductance L, capacitance C, and resistance R of a component. So here, this is the block diagram of the digital LCR meter. Here we have the switching circuit, the linear conversion of inductive impedance into voltage, linear conversion of capacitive impedance into voltage, next the current to voltage converter. There is a phase sensitive detector for the capacitance and the inductive measurements given to IA to D converter. Next is the decade counter, the output of which is given to a digital readout. So here the switching circuit, it may be a manual switch or the automatic inside the semiconducting switch. So for selecting the measurement of inductance, capacitance or resistance, the finding unknown values of above components, the front panel controls of LCR meter has manual or automatic switches whose switch can be changed for required flow of measuring unknown values to switch positions 1, 2, 3 meant for measuring unknown inductance, capacitance, resistance as indicated in this block diagram. Here so the block diagram of digital LCR meter contains the switch circuit, the conversion circuits, the phase sensitive detector, the E to D converter, the decade counter, and the digital readout. So the switching circuit may be manual switch or automatic inside semiconducting switch for finding unknown values of L, C, R components. The front panel controls of LCR meter has manual or automatic switches. We can switch to the required position for measuring unknown inductance, capacitance, resistance. So conversion circuit, this is used for converting the unknown parameter into voltage. Three such circuits are used for measurement of unknown inductance, unknown capacitance and unknown resistance. So this is the circuit for measurement of unknown inductance. Here the conversion circuit is consisting of the op-amp voltage given to a non-inverting terminal and measure the current in inductance L. That is, the current is I through resistor which gives the voltage developed across R. That is, we conclude that the voltage developed across L is directly proportional to the inductive impedance. So you see the diagram here. We have an input voltage source of 1.6 volts at 1 kilohertz given to an op amp. The output of this through an inductor, it is connected to 1 kilo ohm resistor. The output of this is given to a phase sensitive detector to produce the quadrature component and the in phase component. So the conversion circuit consists of op amp to which a known voltage is given to non-inverting terminal, measure the current in unknown inductance L. This current I through resistor R gives the voltage developed across it. So input voltage, supposing it is 1.6 volts, the resistance 1 kilo ohm. So I is 1.6. So VL is I into XL equals to I into 2 pi FL. It is 1 volt RMS. If L is assumed to be 200 millihenries, then VL is equal to 1.6 2 pi FL, 3 volts. So the voltage developed across L is directly proportional to the inductive impedance. Next, this is for measuring the capacitance value. This is the circuit for measuring the capacitance value. The input voltage is developed across the capacitor and the output voltage is measured across the resistor, which indicates that the voltage developed across R is directly proportional to the capacitive impedance. So input voltage is developed across the capacitor and the output voltage is measured across the resistor. So we know I equals to V by XC, VR equals to IR, V is the input voltage 1.6 volts, F is 1 kc, R is 1 kilo ohm, then I equals to V by XC is equal to V into 2 pi FC, which is equal to 1.6 into 2 pi into 1 kilohertz into 0.1 microfarads. Then I is given as 1 milliamp. V equals to I into R is equal to 1 milliamp into 1K equals to 1 volt RMS. The voltage developed across R is directly proportional to the capacitive impedance. So here, for inductance measurement, a transistorized shifter or op-amp shifter circuit is employed to convert the inductor voltage into quadrature component and the in-phase voltage component. In case of capacitance measurement, the phase sensitive detector converts the resistive voltage into quadrature and in-phase components proportional to the capacitive current. So now you see the circuit to measure the unknown resistance. So here we have current to voltage converter, the AD converter, the decade counter, the digital readout. We have an op-amp with unknown resistance in the feedback circuit. The output of the op-amp is given to the A to D converter, the decade counter, and the digital readout. So, for measurement of resistance using digital LCR meter, op-amp has current to voltage converter. Known current is passing through the constant current source, and in feedback path, the unknown resistance R is connected. And when we observe the voltage drop across the unknown resistance, the voltage drop across the resistor is applied to an A to D converter, which converts the analog data to digital values. The standard values are maintained to get the final output as indication for the value of the unknown resistance R. So these are few digital LCR meters which can measure the inductance, the capacitance, the resistance, and transmission factor. The digital LCR meter shown can measure L, C, R, G, and D. The desired function is selected by the push button. The range switch is normally set to the automatic position for convenience. When a number of similar measurements are to be made, it is faster to use the appropriate range instead of the automatic range selection. Four terminals, current and potential are provided for connection of the component to be measured. For general use, each pair of current and voltage terminals are joined together at two spring clips known as Kelvin clips, which facilitate quick connection of components. So bias terminals are also available at the rear of the instrument so that a bias current can be passed through an inductor or a bias voltage applied to a capacitor during the measurement. For R, L and C, the typical measurement accuracies are plus or minus 0.25% plus 1 plus 0.002 R or L or C or G digits. For D, the measurement accuracy is plus or minus 2% plus zero point 0. Resistance measurements may be made directly on the digital LCR instrument over a range of 2 ohms to 2 mega ohms. So resistances between 2 mega ohms and 1000 mega ohms can be measured as conductances, and the resistance calculated as R equals to 1 by G. Conductance is measured over a range of 2 microseconds to 20 microseconds. Conductance is measured over a range of 2 microfarads to 20 farads. Inductance and capacitance measurements may be made directly over a range of 200 microhenries to 200 henries and 200 picofarads to 2000 microfarads respectively. So the dissipation factor D is determined by pressing and holding the D button while L or C button is still selected. Q factor of the inductor is calculated as reciprocal of the dissipation factor. Q equals to omega L by R, which is equal to 1 by T. The Q factor of the capacitor is calculated as the reciprocal of D, which is given as Q equals to omega C R equals to 1 by D. So, we have seen the various blocks of the LCR meter. It is a block diagram and its working and procedure to measure the resistance value, the inductance value, the capacitance value, also the Q factor, the dissipation factor, etc. Now, let us see the specifications of a digital LCR meter. So, when you speak about the specifications of digital LCR meter, it has power supply of 230 volts plus or minus 15%, 50 Hz frequency, the display, 3.5 digit 7 segment LED display, the resolution 0.1 microhenries resolution or 0.1 picofarads or ohms, accuracy plus or minus 1%, the measuring range, inductance is 0 to 2 henries, 5 decades, capacitance 0 to 2 microfarads in 5 decades, resistance 0 to 2 mega ohms in 5 decades. The source is 1 kilohertz for L and C and DC for resistance. The power is 6 watts maximum. The power requirement is AC 230 volts 50 hertz. The dimensions, of course, depends upon the meter which you are procuring. The weight depends upon the meter. So here the variable measured is L or C or R. The measurement frequency 1 kilohertz or 100 hertz. The measurement modes may be serial or the parallel mode. The accuracy is 0.025% of the nominal value. The maximum voltage across component is 0.3 volts RMS. The The sampling rate is 2 per second. The display, it may be a 3.5-digit display. The response time less than 1 second. The power supply is 230 volts at 50 hertz. The size, it as I told you, it depends upon the instrument which you are procuring. The measurement ranges L, you can measure from 0.01 microfarad, 0.01 microhenries to 999 henries. C, you can measure from 0 picofarads to 9999 microfarads, or the resistance value you can measure from 0 to 100 microfarads. Next, the ultimate resolution can be achieved by considering L is 0.1 microhenries, C is 0.1 picofarads, R is 0.001 ohm. The basic accuracy is plus or minus 0.25% of the reading, or plus or minus 1 digit. So we have seen we have seen the block diagram of a digital LCR meter. The